In this video, we'll learn the numpy array. NumPy arrays are used frequently in mathematical operations. They're particularly good for numerical values. It can also handle strings. Here, we will talk about how to define the NumPy array and how to use it. The NumPy arrays, they have a lot of functions defined underneath that. The NumPy array itself, just like a list or tuple, each one of them is a class. And this is a class of those functions that can deal with linear algebra operations, Fourier transforms, matrix operations, and parametric distributions, and so on. The NumPy array object is referred as the ND array. It's good to use the NumPy array because this class, a lot of the functions were written in the C or C++, which is much faster than directly using Python. And beyond that, the values in the ND array are stored in continuous memory. That makes retrieval also faster. To install the NumPy array, if you have not installed, just in your command line or script window, type pip install numpy. If you have a Mac computer and you have the Python 3 and above installed, you might need to use Python 3 pip install numpy. And if you are using Colab, every time you use your Colab, the very beginning, you need to do the exclamation mark pip install for the package with the package name. Okay, once this package is installed, you can use the import numpy as np to use it. Later on, just use this abbreviation np whenever you want to call a function from this array. Here are some examples. With 1D array, you feed into the np.array with a tuple or a list, and then it will convert it to a NumPy array. For a 2D array, you can feed in a nested, look like a nested list here. This 1, 2, 3 is the first row of the 2D array, and 4, 5, 6 is the second row of the 2D array. So if you print A here, this is the A object. If you print A, you will get just those 3 numbers. And if you print B, you can see that the 2D array is shown as with the first row and second row. You can also define higher dimensional arrays. For example, 3D array, you simply just this is a 1D array, and here's another 2D array, another 2D array. The 2D arrays next to each other separated by comma, and beyond that, you put another like a parenthesis for tuple, or you can use the square bracket for list. Either case, this will become the 3D array. So basically for 3D arrays, you're going to have these 3 layers of the nesting when you do the inside to be inside of the np.array command. And this could be tuple or list or mix of the two. So for the 3D array, this 1, 2 is treated as the first row of the first 2D array. 3, 4 is the second row. So together, 1, 2, and 3, 4, that's the first 2D array here. And then the 5, 6, 7, 8 would be treated as the second 2D array. If you imagine how these 2D arrays are located, you can think of the 1, 2, 3, 4 as one sheet of the data, and then 5, 6, 7, 8 as another sheet of data that's behind of this first sheet. We can access the elements of NP arrays just like we did with the index, with the list or with tuple using indexes. With the 3D array, for example, if you want to access one single value, then you need 3 indices because it's a 3D array. And if you want to access the part of that, for example, you just want to access this part. This is in the first of the 2D array on the second row. So in that case, you can use the index 0 to tell it's the first 2D array, and then the 1 here for the second row. You did not provide the third index. That's why this 2 and 4 together are taken out. And say if you only want to access one value, the 3 alone, in that case, just provide another index 0 for it. Again, here, all the zeros are used. That's because the index start with 0, just like for index for the list and for tuples. This way of providing 3 indices will reach the individual number, but you don't have to do it that way. You could also first pull out this subarray and then provide a single index to take out the if you first take out this subarray and then you take a single index, you could also take one value out. Let me say, suppose I have this one, and that is inside of here. And if I try to run it, that's my D. And then afterward, I want to take the D, the 0 and the 1. This is supposed to take out the 1, 2, 3, 4, that the subarray. And then I put another square bracket and 0. That should give me the same answer. Okay, run this one to see. Oops. End of line while passing. Okay, so I'm missing a parenthesis in the print command. You see this value 3 is taken out. That's because this part take out the 3 and 4, and then you take one value. So use the 0 to take out the first value of the 2. Okay, that's this indices. And for indexing, we could actually use this kind of 3 indices to give us the start and the end, also the increment to get a slice of the array values. For this notation, for example, like this here, I have the import and I have a range from 2 to 11. That means that the value 2, 3, 4 all the way until 10. The printed value, you can see it from 2 to 10. And if I want to take out the 2, 4, 6, 8, and 10, I could just provide the 0 for the start, which is this first start index is 0. And then the step, because I want to have 2 and 4 and 6 and so on, so the step need to be 2. And because I also wanted the 10, then the last one, the end index, I will need to provide something that's basically the length of this array. But if you want to put the length of the array, you can just skip that. So we use a colon, and you skip the end index, and then you put colon 2. That'll take out the 2, 4, 6, 8, 10. Okay. If for any of these indices, the 3, the start, the end, and the step, the step is not allowed to be negative. The start and the end, if you use a negative value, that means that it's counting from the tail. If you use negative value, it's counting from the tail side. And if any one of them is missing, for example, if this start index is missing, then it's always interpreted as 0. Or if the end index is missing, it would always be treated as the length of the array. And if the step is missing, it will by default using value of 1. Let's see more example. For the example of range 5, that's the value 0, 1, 2, 3, 4, and we make it into an NP array. And then afterward, we can use this 1, 5, 2 to take out this first value, third value, and we want to take also the fifth value. But since we put the, okay, with 5, we put the 5 there, then the 5 could not be included. Therefore, this becomes just 1 and 3. So index 1, index 3. And then that's it. So index 1, you get this value. And index 3, you get this value. Okay. So that's why we get 1 and 3. And if we put in the -3 to -1, that means start from the end. This is 1, -1, and -2. But it's not, just a second, -3, sorry, -3. Here's 1, 2, 3. So this part is the -3. And then here's the -2. And here's the -1. Because the beginning is included, the end is not included. That's why it's taking out the 2 and 3. And for this one, A with the index colon 2, that will simply just do 0 to 2. So 0 to 2 give us the first 2 values. And here the 2 colon means from 2 all the way until the end. That includes the last value. So for this array, the last value is 4, and then we'll have 2 to okay, the length, the missing one means interpreted, missing end interpreted as the length. The length is 5, so 2 to 5, and this 5 is not included. That's why you see the 2, 3, and 4 in there. And we put a -1 just to take the last value. Okay. Slicing for the 2D array is similar. Here's an example. We have the first row of a 2D array being these negative values, and second row are these positive values, and the printed array looks like this. And if we wanted the -2 to -1 for the second index and the first index being 0, that means we're looking at just this row, and -2 to -1 means from the tail. We'll start from here and not including the -1. Therefore, what you see is just -2 being taken out. And for the next example, just change this first index to 1. That will take out the second row and take this value. And if we put 0 to 2, that means both the index being 0 and 1 are included. So we essentially, what we take out is the second column of the 2D array. The Python data type and the numpy data type, they are different. Different in the sense that for Python data type, we only have these strings, integers, and the float, and the logical Boolean type, or complex numbers. But for the numpy array, there are more detailed types. I for integer, and B for the Boolean, means logical values, true or false, and U means the unsigned integer. The integer versus unsigned integer. These unsigned integers are just positive ones. If you have the same number of digits to store the number, this unsigned integer would allow to have every bit to be used for a number. But if it's an integer, you have to keep one of that to use it to store the sign, positive or negative sign. Therefore, the integer versus unsigned integer, if same amount of storage space, then the unsigned integer, the maximum value would be about twice of the signed integer. And F here is for the float, and C for complex float, and M for the change in time means the time delta. When you have two time provided and you are looking at the difference between the two time. And the next one is just the date and time, capital M. And O here is for just any arbitrary object that could be complicated different types. And S here is for compatibility that's used for the Python 2. And this S is particularly referring to the zero terminated byte. What's zero terminated byte? So when you store a string, what we see is just the string, but inside of the computer, when it's stored. For Python 2, it was not stored as just the string. Instead, it was padding a zero at the end. So it's like a pad of zero extra there. That's the zero terminated byte. And the U here means a Unicode string. For all of the Python 3, like 3.1 and above, all these Python 3, the strings are stored as Unicode. So it's in the format with the U here, the U type, okay. The V for it's just a memory, a fixed chunk of memory to be used for other things. And regarding this Unicode versus the zero terminated byte, Unicode is more convenient and it stores more information. Actually, Unicode is the only one that that could actually store for every language. I mean, this Unicode is the only kind of character encoding standard that assign a code to almost every character in every language in the world. And depending on how long is how many bits are used to store a character, the Unicode quite often you can see the UTF-8, UTF-16, UTF-32. For UTF-8, that means it would use the base unit would be 8 byte. And for example, if one character can be stored in the 8 byte, then it will just be the 8 byte. If we cannot, then they will need to use double of those 8 byte, which becomes the 16 bit. I'm sorry, 8 bit. Or if 8 bit is not enough, then they need to use 16 bit. So what is a bit? A bit is just storing either the 0 or 1. That's a bit. So 8 bit would be storing at most of 2 to the power of 8, which contains 64 characters. And if it's in the table is more than the 64, then the next one need to start to use another 8 bit to help to store. So it will have a total of, in fact, total there are these 4 of those bytes needed to store all of those possible characters. So for UTF-8, a character is stored with using either 8-bit or 16-bit or 24-bit or 32-bit. So it's always in the multiple of the 8-bit. And every 8-bit is actually 1 byte. 1 byte contains 8 bit. So in other words, this one, the base unit is like a 1 byte. And if it's not enough, it's going to use 2 bytes or 3 bytes or 4 bytes to store it. And for the UTF-16, the base amount is 16 bit, which is equivalent to 2 bytes. And that's the base, regardless of whether the character is in the beginning of the table. For example, just the first one. For the first one, of course, it doesn't need that many digits, but unfortunately, because you decided to use the 16-bit, it will still occupy 16 bits to just store that first value. But once it goes more than the amount that can be considered, can be included within the 16-bit, it will start to use the next 16-bit. So it will be either 16-bit or 32-bit. So if we convert it to byte, this UTF-16 would be using the 2 bytes or 4 bytes. And UTF-32, on the other hand, store all of the characters using 32 bits, which means always use 4 bytes to store any of the character. And you know that we'll have a lot of waste. The UTF-8 is the most commonly used encoding. So here is the numpy data type example. DT start with np.d type with I4. And this means that when we have a I means the integer, F float, C means the complex number. And what's behind of that is the number of byte. So if we have a I4, that means 4 byte, and each byte contains 8 bit. So the total would be 32 bit. That's integer. And this one is 8 byte, and each byte contains 8 bits. Total would be 64 bits. So it's a 64-bit floating point number. And this one would be the 16 byte times, if you multiply by 8, it becomes 128-bit complex number. That's if you have integer, float, or complex number. But if you have a string, you can use A or S for those zero-terminated string. If we put A25, that means you're going to have 25 characters. The last one is 0. On the other hand, if you do the U25, that means it's a character string with 25 characters, and is based on the Unicode. Okay. So in summary, when we have this D type, the data type, the first letter indicate what type of the object it is, and the second one specifies how many of the byte it will be used to store that number, except if it's for string. For the string, it just tells you how many of the characters are in there. Example here. Let's say we define a numpy array. This is a 2D array. And then we want to look at its data type, and we use this b.d type. And it shows as int32. This int32 is the same as the I4. When it specifies the entire word int rather than the I, then this becomes the bit, okay, 32-bit. Or the I4 means the 4 byte. And this one, we have one value being -1.2, the rest of them are integers. When this happens, it will try to convert to all of these numbers to the same type of the highest one. Like this one becomes the dominant type for the entire array. So if we look at the .d type, it tells us it's a float number. In Python, the default would be all 16-bit. That's why you see it's float 64, which is equivalent to those F8 we saw on the previous slide. Similarly, in R, it's also default 64-bit, which basically means that all of these numerical values are treated as double precision. This next example, you have the integers, and in addition, you also have a string here because of quotation mark. Once you have a string, in that case, the entire array becomes a string. So if I put the b.d type, then you can see its type. And the printed output is this less U11. Less means it's the little ending. And if you see the printed as the greater, that means the big ending. What's the less and big 4. The less means that for the little ending, it will try to, in this case, it has the 4 byte, and the first 2 byte and the next 2 byte indicate whether the first 2 byte is for the smaller part or the most significant digit, or for the least significant digit. Okay, so this is the default. Default is supposed to be the UTF-8. Okay, UTF-8. And inside of the UTF-8, this has 11 characters, and the way to store these characters is that each character, it is using the 2 of those. Here this one is the UTF-8. Is actually 16. So each one of them are using the 2 of those bytes, and the most significant 2 versus the least significant 2. And the most significant 2, if it's for the small ending, and the most significant ones are goes in the later part. On the other hand, for the big ending, the most significant bytes are in the smaller address. So basically, imagine you have the address like this, and here the address goes, for example, that's the 0x, and then the 1, 2, 3, 4. Oh. Your X 1, 2, 3, 4. This 1, 2 is for one part of the character. 3, 4 is for the other part of the character. The 1, 2, and 3, 4 together is for one character. And this 1, 2, 3, 4, depending on whether it's the small ending or big ending, this 1, 2 this is the smaller address, and here's the bigger address. And if you are using the big ending, that means that this leading part, this part is the most significant digit. That's for the big ending. And for the small ending, it's the opposite. You put the most significant ones in the end, like put it over here. This is for the small ending, the most significant one. And so 1, 2, and 3, 4 will become 3, 4, 1, 2. For every character, it will switch the 2, small ending versus the big ending. Okay. To us, mostly it's not really important because we don't really deal with that much detail ourselves. So instead, as long as you recognize it's the Unicode with 11 characters, then that's fine. That's sufficient. Okay. So that's for this numpy array with different data types. Here, this is this slide tells about we could actually use this D type to help to change the type if it is possible. What do I mean by possible? If you have, for example, these 5, 7, 2, 3, they are in character strings, but you want to convert them into integers. In this case, you can specify it as np.array and then specify the D type equals I4. This will convert these strings to integer. But if you have something, for example, a quotation mark and an actual inside, we will have a character. In that case, then you try to do the I4, then it will fail. It will have an error because the W itself cannot be converted to a numerical value. We could also use this D type to change the data type to, for example, say we have these float numbers 1.1, 0.1, and so on inside of the NP array. But what we want is an integer array rather than this float array. In that case, we could specify the d type equals this I to convert it to integer. So once we have this one in there, if you print it, this 1.1 will be converted to 1, and 2 stays as 2, -3 is -3, and 0.1 becomes 0. In this slide, I missed the 0, so I need to add the 0 here. Beyond using the d type inside of the np.array command, you can also use this nd array object with the dot as type to change it to another type. For example, I'm putting the bool, B-O-O-L, to specify that I want to convert these values to logical values. Numerical value to logical value will be converted in a way such that any of the non-zero values will become true, 0 values will become false. So in this case, and previously it was integer, 1, 2, -3, -3, and 0. And now one will specify as the bool, so the first 3 values are true, the last one is false. For next, let's talk about the different available functions for the numpy array. And this slide tells about the copy versus the view of a numpy array. If you have an object A, for example, here we have A being NP array, and then you can use A.copy to get a copy of this A. This copy is actually a copy. What I mean is A, you can imagine, is the original content. And this A is like you copied from the copy machine. And later on, when you, let's say we assign the A.copy to X, then this X is actually a different copy. You do whatever to the X is not affecting the original A. So for example, I will make X0 equals 10. And if I print the A, it's still the same as the original one, 1, 2, 3, 4, 5. But if I print the X, the first value becomes 10. And that's for the copy. On the other hand, the dot view, if you do the dot view, this is just like you're looking at the original array. And this dot view, when you try to assign it to an object, for example, make this A dot view, parentheses equal to Y, make it assigned to Y. In that case, this Y is pointing exactly to the same object A that you defined originally. So if you change the Y, you are also changing the A. You can think of the view as if, for example, your friend has a jewelry, and the view is like you borrowed the jewelry to have a look at it. And let's say, for example, you accidentally damaged the jewelry by breaking it when you pull it. And then this broken jewelry is the one that your friend has, even though right now you are holding it. So even though you borrowed it and you broke it, and the one that your friend had is exactly the same one, therefore, this change that you made to the jewelry also changed your friend's jewelry. So like this example, I assigned A.view to Y, and then afterward, we make the initial value to be -8. So that changed the initial value. If I print the A, it shows that the first value becomes -8. And if you print the Y, this Y also shows that the first value becomes -8. By the way, when you put this quotation mark /n, that means is the new line symbol, is the return. And in the print command, it basically means that you printed the first one and you print a return line, and then a next one follows afterward. So that's the copy versus the view. The next function is a concatenate. concatenate would allow to concatenate the values in the numpy array. And how do we concatenate in the row, in the column, or in the further dimension? That depends on the axis. If you do not specify axis, it will treat it as axis 0. Here, let's see, for example, A is an NP array with 1, 2, 3, and B contains 4, 5, 6. When we do the NP dot concatenate, that'll put them just next to each other, becomes a single array, 1, 2, 3, 4, 5, 6. Let's say another example for a 2D array. If you have 1, 2, 3, 4 as one array, that's the 2D array. And 5, 6, 7, 8, that's another 2D array, okay, A and B. And when you try to concatenate X is 0, that means that you are going to put it along the row. Along the row, concatenate along the row, then you see 1, 2, 3, 4, 5, 6, 7, 8 together. So you put it together along the row, it becomes a 2D array, but now contains 4 rows rather than the original 2 rows. Okay, the next one, put X is equals 1, that means you concatenate along the column. So originally this 1, 2, 3, 4 is the first array, and now you concatenate along the column X is equals 1, so you put the other one next to it. In the end, what you get is an array with 2 rows, 4 columns. Beyond this concatenate, there are also like a few others that could concatenate the arrays. One of them is called the stack, but this will create a new axis rather than the original number of dimensions. For example, we have A being a 2D array, B is another 2D array, and then we use the np.stack with AB. This AB need to be in parentheses or in square bracket so that it's a sequence, one object, okay? So we have the A and B together as one object sequence, and then we have X is equals 0. In this case, it will become a 3D array. So the first sheet is provided by A, the second sheet provided by B. So you can see here the 3D array that has 1, 2, 3, 4 is the first part of the array, and 5, 6, 7, 8 is the next sheet of the array. And when we try to do X is equals 1, in this case, it will try to take the first column of the A and then the first column of the B and then put them together. First column of, let's see, the A here. So when we do the X is equals 1 here, it will start to do take the value, okay, it's 1 and the 5, and then the 2 and the 6, and then the 3 and 7 and the 4 and 8. Afterward, arrange them into the array. Okay. So when you put them into the array, now becomes this 1, 5 here, 2, 6. Maybe I did not explain well, but actually I feel this np.stack axis with the axis is always confusing. The best way is to avoid this np.stack. Instead, you can use this h-stack, v-stack, or the d-stack to achieve that. H means horizontally stack, and V for vertically stack, D for stack in depth. Example here, we have A and B, each one being a 2D array, and H-stack simply just put them side by side next to each other horizontally. And V-stack, we just put them one above the other, becomes vertically stacked together. And the D-stack will achieve the depth there. So that take out so for the depth, it will take the 1, 2, and 5, 6 together Yeah, 1 and 2, that's the first one, and 5, 6 in terms of depth, I put together as one sheet. And then the other one is this 3, 4, and 7, 8 together as one sheet. So that's for the stacking them. The most frequently used command in this stacking is the H stack or the V stack. The dimension of these numpy arrays, they could be changed. For example, if we have this NP array, this is a 2D array, and you can use that shape to see what's the dimension. It shows like 2, 2, 2, means 2 rows, 2 columns, and the other third dimension has the 2. And then you can change to other shape. You use the dot reshape command to do that. Whenever you try to do that, it will first collect all the numbers and rearrange it based on the new dimension. So here, the 2 to 4, that reshape with 2 and 4, that means first collect all these numbers. You know, in R, when you collect the numbers in an array, you will go column-wise, but in the Python, it's going to collect numbers in row. So it will do 1, 2, 3, 4, and then the -1, -2, -3, -4. That's the flat ones without the dimension. And then afterward, it will arrange based on the dimension specified in the reshape. So if you have 2 and 4, that means 2 rows. Each row contains 4 values. So we'll put the 1, 2, 3, 4 as the first row, and the remaining for the second row. So that's the reshape command. So whenever you use the reshape command, always be careful about keeping in mind that it operates row-wise. Here's more example. If you do the reshape, and in the reshape, you don't really know the total number of values in the entire array. In that case, you can leave one of the dimensions, one of them to be -1. Doing so will basically do the automatic calculation. For example, if you do G dot reshape with the 2 and -1, that basically says that I want 2 rows. As far as how many columns, compute for me. So based on the total numbers divided by 2, that'll be the number of columns. Okay, similarly, if you just want to convert it to 1D array, in that case, just directly put in one number with -1, and then I'll just directly put whatever number in there becomes a 1D array. Or you can use this dot flatten. It will achieve the same effect. So it's either the dot reshape with -1 or dot flatten parentheses will convert the entire array into just 1D array. How do we loop through an array? That depends on what do you want to loop through. When you have an n-dimensional array, if you're just taking single loop, then it will basically go through each of the n-1 dimensional array. For example, let's say A is a 2D array here, okay, in this example, a 2D array. And then when we do the for loop, it will go with the next dimension. So it's like 1, 2 being together, that's I equals 0. And I equals 1, it will give us the 3, 4. The next example here, the G being a 2D array. And for that 2D array, if we want to go through the loop, X in G, in this case, it will treat this part as for X equals 1, the first one. And this is the next one when you go through it. So when we try to print here, just for us to see, I'm putting also triple stars in the print. You see the triple star and 1, 2, 3, 4. And then the triple star again for the next X value, that's the next 2D array. Okay, that's for looping. So basically, a single variable in the for loop will only go through the reduce one dimension from the 1D array to loop through. And if you want to loop through individual elements, you can do it by nested loop. For example, like this one, if we want to go through this 2D array, then we can do, oh, sorry, that's a 3D array. This A is the 2D array. If we want to go through every element in this 2D array, we can use double for loop. So one for loop goes through the row being the 0, row being the 1, and another one goes through the column being 0 and 1. So we first go through the row x in A. This x will take the first row of A and take the second row of A. So for each of the x, we'll use the y to go through each entry in that row. So that'll give us these 1, 2, 3, 4. Similarly, other than this double for loop, you can also use this nd nd iter for iteration. ND array iteration. So in this case, it will just go through the members in this array. So basically, it will go through every member inside of that array, just like in the nested loop. If you have a 3D array, this single .nd iter will go through every entries in the 3D array too. Suppose what if you want both the index and the element of the array? In that case, you would use the double variables, two variables. One is the index, the other one is the value. And then you use this .nd enumerate, okay. So with that, what will happen is you have the index and also the element being returned. So here, if I do print I and the x, I'm putting a colon just to separate to tell that what are the I, what are the x. Here's the output. This is the index at 0, 0. That means that at because here we have A being the 2D array, so there are two indexes, the row index and column index. So this is the first row, first column, and that value is 1. Similarly, for the others, you see the index and also the value. So that's doing the ND enumerate. So let's try with this 3D example for the G here. So previously we had this 3D example. Let me try to get this G, and we want to get both the index and the value. Let me put it here. So that's my G. And I want to go through the for loop for the index I and the value X in G dot ND enumerate, ENUMERATE. Sorry, ND enumerate that with the G in it. NP dot enumerate with the G in it. And then afterward, the colon to start the for loop. And inside, we're going to print the I. And this time, let me put the quotation mark. I will put this tilde just so that I will know it's tilde there. Okay. And then afterward, let's put in the X value. Okay, so let's see. If we run this, what do we get for our index? It's a 3D array. For 3D array, we should have 3 of these indices. So you see 0, 0, 0, and then gives the double tilde and the value 1. So that tells us add the row, column, and the sheet index. Sorry, this is the sheet and the row and the column. So that's the ND array to enumerate. If you want both the index and the value, you use this NP data ND enumerate. If you only want the value, you use NP data ND iter. If you want to do it by double nested for loop, you can also do that. There are many functions defined. We only went through a few of those, and on the next few slides, it listed the functions available for these numpy arrays. And some of them are used frequently, and some are I have never used. This one, for example, np.all. this would be np.all. That basically check if all of them are true. So it will return true if all the elements are going to return true. And np.any, let's check if any of the elements is true, np.any. And np.argmax, that'll give us the index such that the value being maximum. So that's np.max. And the next one, np.argmin, to give the index such that the value is the minimum. This np.argshort would also work. I mean, return the indices, and this index will, if you use that index, you will get the sorted array. Okay. np.as type we already tried, and this np.clip. Clip is to truncate the value based on the minimum maximum specified here. For example, you have a value that computed to be too large, that's 10 to the power of 20, that kind of value, but you don't want it to be stored like that. If that happens, you know the computation has something wrong. So you want to truncate it to 10 to the power of 10. So in that case, you can specify minimum to be, for example, a small value, negative value, and the maximum just specify to be the 1e plus 10. That's the np.clip. And then there's np.copy, we already saw that. And then this np.cum means the cumulative product. Just multiply all the numbers together. Sorry, cumulative. Start from the first value, and then first value multiply second value, and the first value multiply second, multiply third value, and so on. And next one is the cum sum, cumulative sum. Is to compute the sum of the first consecutive values, like the first value. Let me try it. Okay. Like the sum of the first one, and then sum of the first and second, and sum of the first, second, and third, and so on. So let's say I have this. Do I have the A here? I still have the A. Okay, that's my A. Then I want to do np.cum sum, cumulative sum. I want to do that. Okay, I need to do the print. So that gives the printed value of the cum sum. Okay, let me also print the age so that we'll see. A itself contains 2, 3, 4, and so on. And then when we do the cumulative sum, this first one is just the first value itself. The second one is the sum of the first two values. So 2 plus 3 gives us 5. And this is the sum of cumulative sum of the first three values. So those sum together give us 9. And this is the sum of the first 4 values, and so on. Similarly, if we had computed the cumulative np cum product, PROD, of A, that'll give us the cumulative product. Like this is the product of the first value, which is itself, and this is the product of the first two values, 2 and 3. And this is the product of the first three values, and so on. Okay. The diagonal here will take out the diagonal entries, specify the diagonals, and the dot here computed that product of two arrays, dot product. np.max computed the maximum, find the maximum, and np.min do the calculating of average, np.min find the minimum, and np.prod just compute the product for given axis. And others like np.sort is to sort the values, and np.reshape. Sometimes we also use np.repeat for basically duplicate the numbers. np.sum is to compute the summation of the values, and there are also these np.var to compute the sample variance, and np.sd. SD will here is the STD is standard deviation. Okay, np.std. Yeah, these are the things that we use pretty often. That view we already mentioned. You do not need to be totally familiar with all of them. So roughly, all you need is to know what are available. And when you need, you search the help file of each one of them. For example, this np.transpose is to transpose an array. For example, a matrix, you need to do the transpose before you do inverse and so on. Then this np.transpose will serve that purpose. And how do we find that? You can just search online np.transpose or numpy.transpose, and then you look at the help file. Okay, so that's about the numpy array. In summary, the numpy array is a class of objects that's written in C or C++ behind, but for us, we can just operate it directly in Python, and it's convenient and in the sense that we can operate the entire array easily. For example, let's say our A is given by these numbers, and I can easily compute the exp e to the power np.exp of A, and that will just do element-wise operation for all of them. But if you had a list, on the other hand, you have to operate one at a time in the for loop. This is just one example. You can actually do quite many of those operations directly with this manner. Essentially, this NP array object behaves similarly in R, like the vector or the matrix or array object is the entire object. Okay, and whenever you need to use a function of this type of object, you use the NP with the dot and the name of the function. Okay, that's all for this NP array.